残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
Bow, calculus. All right, back with another bit of calculus, learning today about the mean value theorem. All right, the mean value theorem is a cornerstone in the theoretical framework of calculus. Several critical theorems, some that we've talked about previously, rely on the mean value theorem in a deep and important way. This theorem also appears in a lot of practical applications. Let's start with a preliminary result known as Rolle's theorem. So Rolle's theorem says that if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b with f of a equal to f of b, then there's at least one point c in the open interval from a to b such that f prime of c is equal to 0. This is a lot easier to see with a picture. So I've started to sketch one over here. I've got some kind of a curve right here. This is y equals f of x, that white curve there. Okay. Now, if I'm looking from, say, let's start here. And let's call this bad boy A. And let's call this bad boy over here B. Then, what we're seeing from this is that this is f of A. And that's also f of b, i.e., from a to b, this thing doesn't go up or down at all. It starts at the same height it ends at. All right, so the gist of it is that if the function is differentiable between a and b, potentially not at a and b themselves, maybe we don't even have a function, maybe the function isn't even defined past there, so we could lose the two-sided limit necessary for differentiability. But as long as it's differentiable between a and b, potentially not at the endpoints, and those endpoints are at the same height, then here's the whole idea of it. If you went up, you have to come back down, and if you went down, you have to come back up. If you end at the same height that you started at, it doesn't matter how far you went up or how far you went down. You have to go the opposite direction of whatever you've done to get back to where you started. All right, and naturally, if a function is differentiable, then that place where you stop going up and you start going down, or you stop going down and you start going up, you have to have a zero derivative right there. All right, fair enough. Let's look at an example to see how this all really works. Build some more intuition. Okay, let's try out a real-world type of example. So imagine you're looking down on a road like this, or even better, imagine you're driving in your car. Let's say that this car right here is us. All right, so I'm just going to draw a horizontal line, or at least pretty close, across and get something like that. All right, switching colors just to keep everything very clear and legible. So here, let me make that even a little bit brighter. There we go. All right. So if you start here, think about the direction that you're looking. This is essentially what the tangent line's telling you. If we're thinking of this road as the graph of a function, then the derivative is telling you the slope of the line that is passing through your car as you're driving down that road, right? I.e., where you're looking straight ahead, if you plotted this relative to some fixed coordinate system, then where you're looking is in the direction of the tangent line. So as you drive along this road, you end up looking ahead of you in a variety of different ways. Variety of different directions depending on where you're driving at any given moment. But notice that if you start here and you end here, same height on this picture, right? Then at some point as you're going along, actually right about where this guy is, or about up here-ish, you would end up with a tangent line, i.e., you're looking in the exact same direction, is where you ultimately end up after the place you started. So maybe I said that a little bit strange. Let's make this a little bit bigger so we can really get a sense of what's going on. So you start here, we're going to end here. We're just picking these points arbitrarily. All right, so as you drive, notice if you started here and you're ending here, you could consider a straight line path between the two. If the road ran just like this, you could go straight from one to the other, never taking your eyes off the destination. But this road's a little bit curvy. You have to take your eyes off the destination because sometimes you're not driving towards it. What Rolle's theorem says, though, is that at some point, you are looking in the same direction as your destination, just translated up or down a little bit, i.e., your eyes are pointed in the same direction as they would be if you were just traveling along the same, or just a straight path, but you've maybe been translated up or down a little bit from that path. So you're going different ways, you're looking different ways, but at some point, you're looking at the same angle relative to your destination. So this is what it's saying. Here and about over here, your eyes would be pointing in exactly the same direction as your eyes would be pointing if you were just going on a straight path. And notice, these are the places where you stop going down and you start going up, and you stop going up and you start going down. So really, and this is a very, very useful metaphor throughout pretty much all of calculus, think of tangent lines as where you're looking if you're driving down a road. Think of the graph of a function as a road. Think of the tangent line as the direction that you're looking if you're looking straight ahead. Okay, cool. Let's move on to the mean value theorem, which, as we'll see in just a moment, is really exactly the same thing. Okay, on to the heart of the section, the mean value theorem. If f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there is at least one point c in the open interval from a to b such that the derivative of f at c is equal to the average rate of change of f over that interval, i.e. f of b minus f of a over b minus a. Another way of looking at it is that the derivative is equal to the slope of the secant line at some point in that interval, in the open interval from a to b. So if you draw a line from f of a, or a f of a to b f of b, those 2 points from a to b, right? Here you got a right down here, just to make everything super clear. That's really where a is, and this is really where b is. Naturally, that tells you that over here you have f of a, and over here, oh gosh, that's a long line to draw. It's going to be sloppy. There you go. You have f of b, All right. So, if you draw a line from these 2 points, then this guy has a slope of precisely this value, f of b minus f of a over b minus a, i.e. the rise, the distance from f of b to f of a, which is f of b minus f of a, over the run, which is b minus a, this distance right there. Okay, what we're saying with the mean value theorem is that the instantaneous rate of change over an interval, the instantaneous rate of change at some point in the interval is equal to the average rate of change over the whole interval. This makes some sense. Just think of it like this. If I said, on average, I was driving 60 miles an hour for the last hour, and I also told you that at no point during the last hour did I actually drive 60 miles per hour, that wouldn't make any sense. i.e., if I say that I drove 60 miles per hour on average for the last hour, then you know that at some point in the last hour I was driving 60 miles an hour. I might have been driving faster sometimes. I also might have been driving slower, but I certainly can't average 60 miles per hour if I never drive 60 miles per hour. This is exactly what's going on here. We're saying that the average rate of change over the whole interval is the same as the instantaneous rate of change at least some point in the interval for a function which is differentiable on the open interval right there and continuous on the closed interval. Okay, so what's going on here? Is this really the same as Rolle's theorem? Well, let's look at a little picture to see exactly what's happening. Really, the mean value theorem and Rolle's theorem aren't different at all. i.e., just look at them like this right now, and then tilt your head sideways on either one of the pictures. More precisely, notice this guy and this guy only differ by a little tilt. That is, take the mean value theorem's picture right over here and tilt your head. It's Rolle's theorem, just with the axes slightly different. These guys are saying the same thing. One way of looking at it is that the mean value theorem gives Rolle's theorem as a consequence in a certain sense, i.e., if the average rate of change of the function over an interval is equal to the derivative of the function at some point in the interval, then if the average rate of change is 0, this just says that there is some point where the derivative is equal to 0 in there. Okay. In the opposite direction, this guy, Rolle's theorem, pretty much tells you that the mean value theorem is true if you just tilt your head a little bit, i.e. just move the picture sideways, and you get this result from that one. This is sort of a good theme throughout mathematics. You can see this not just in calculus, but all over the place. If something is pretty much the same, just up to a slight relabeling, then all of the properties pretty much have to follow through. They all have to be true in both places if they're true in one of them, up to just some relabeling in the other one. Okay, so Rolle's theorem and the mean value theorem are not really so different. They're as different as a picture of you and a picture of you turned sideways. So there you go. Let's try out some actual problems involving these two theorems. Okay, on to our first example. Example 5. Let's find an interval I on which Rolle's theorem applies to the function f of x equals x cubed minus 7x squared plus 10x. Then, based on the interval we've chosen, let's find all points c in that interval at which f prime of c is equal to 0. So, let's start it off. Because f is a polynomial, it is everywhere continuous and differentiable. Now, stop. At first, it seems like this is a non sequitur. Why are we talking about whether or not f is continuous or differentiable anywhere? It's because Rolle's theorem requires continuity on a closed interval and differentiability on an open interval. What this statement here is telling us is that it doesn't matter which interval we choose. We'll automatically get those properties. So we only need to focus on the other properties we want our interval to have relative to our function, i.e., we need an interval AB with the property that f of a is equal to f of b, because we've already got the continuity and differentiability covered. Notice for different types of functions, things like rational functions or, like an absolute value or something like that, we might need to be a little bit more careful. But here, for polynomials, this is pretty easy. So we need to find a place, an interval from a to b, where f of a is equal to f of b. One relatively easy way to do this is by factoring. So let's notice that every term in f right here has an x in it, yeah? So let's pull an x out. Okay, that gives us x times x squared minus 7x plus 10. Good stuff. Okay, and now, if I want to factor x squared minus 7x plus 10, all I have to do is notice that negative 2 times negative 5 is equal to 10, and minus 2 plus minus 5 equals minus 7. So x times x minus 2 times x minus 5, and we're factored. We're all into linear factors. So nice, we factored this guy out, and we can see that the zeros of our function, the roots of f, occur when x is 0, x is 2, or x is 5. We can choose any pair of these these values. We could choose 0 and 2, we could choose 0 and 5, we could choose 2 and 5. Doesn't matter which one. Just for the example, let's choose 0 to 5. And this is because, like we just said, f of 0 is equal to f of 5, and both those guys are 0. So it's totally possible to have other intervals. It's just relatively easy in this case to factor our polynomial and find its roots. Since it has more than one root, this gives us a place where f of a equals f of b, i.e. if there's more than one place where the function is 0, we found somewhere where this works. But there's no requirement that either f of a or f of b has to be 0. You could also find an interval where f of a equals f of b equals 69. Who cares? Any number you want. Now, though, we found, using our factorization, an interval where f of a equals f of b. We've got continuity and differentiability, so we're pretty much good to go. All we need to do now is find points C in the open interval from 0 to 5, at which f prime of c equals 0. This is just the familiar task, the same thing we're always doing. We're just finding critical points of f. So we need to take a derivative. Since f of x is x to the third minus 7x squared plus 10x, the derivative of f is 3x squared minus 14x plus 10. This is just an application of the power rule. All right, set that guy equal to 0. We could try to factor this out, or we could just use the quadratic formula, which, if everyone remembers, is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And this is for equations of the form ax squared plus bx plus c equals 0. These are the solutions to that equation. So we do this, we check it out, and we get that x is equal to 7 plus or minus the square root of 19 over 3. Punch this in a calculator. You get something like 0.88 or something like 3.79. So there are 2 points at which the tangent line is horizontal. Now notice, both of these guys are in the interval from 0 to 5. However, if I had chosen, say, the interval from 0 to 2, which is also perfectly reasonable since f of 0 equals f of 2 equals 0, then while I would have gotten the same things when I took the derivative, the same solutions, one of them would no longer have been valid, i.e., this guy here, if I had chosen instead the interval from 0 to 2, since f of 0 equals f of 2 equals 0, then this guy, this is not in 0, 2. So we wouldn't have used it, i.e. Rolle's theorem doesn't guarantee that this guy exists for the interval from 0 to 2, right? Okay, but this guy's still in there. So Rolle's theorem's still true, nothing is going wrong. And if you want, we can look really quickly at the graph of this function just to see what's happening. So let's flip on over. Okay, now I've got the graph of the function right here, and I'm just going to throw in x equals 0 and x equals 5, put some vertical lines in there to make everything a little bit easy to see. All right, I've taken the liberty of putting the derivative already in here, so I can trace everything around. And notice, since going from 0 to 5, my function is passing through the same horizontal line, i.e. the line y equals 0, what Rolle's theorem is promising us is that there's a place where this tangent line is horizontal. Now, it's hard to get on there very specifically with this, but you can see that it's somewhere right around in there, yeah? And right around down here. Now, like we said before, we could have also chosen to take the interval from, say, 0 to 2. Hey, look, there's still a 0 derivative in there. I could have taken the interval from 2 to 5. Oh, a 0 derivative in there as well. What this is telling us, and this is actually pretty cool, this is neat. Rolle's theorem tells us that the roots of a polynomial, the zeros of a polynomial, are interlaced with the zeros of the derivative, i.e. the zeros of the derivative happen between the zeros of the polynomial. That's pretty cool. So here I've got a 0, here I've got a 0 for my function, my polynomial right here, yeah? And if I look at the derivative, notice, and here I'm just tracing the tangent line across, but notice the tangent line turns horizontal right about in there, yeah? That's a 0 of the derivative, and that is between two zeros of my polynomial. Similarly, I have a 0 of my derivative down here, and that's once again between two zeros of the polynomial. Huh, kinda cool. Weird. All right, we'll do another example. Okay, another example, this time with the mean value theorem. So, example 6. Determine whether the function f of x equals 2x to the third minus 3x plus 1 satisfies the conditions of the mean value theorem on the interval from -2 to 2, including the endpoints. If so, let's find the points guaranteed to exist by the mean value theorem. So, to start, f is a polynomial. It's everywhere continuous and differentiable. So, it certainly satisfies the conditions of the mean value theorem on the closed interval from -2 to 2. Once again, the mean value theorem requires continuity on a closed interval and differentiability on that interval but without the endpoints. So we've shown that at least f is a candidate to have the mean value theorem apply. In fact, we've shown that the mean value theorem must apply since f is continuous in this closed interval and is differentiable on the open interval from -2 to 2. Yeah? Cool. All right, so the first step is to calculate the average rate of change of f on this interval, since, the mean value theorem says that there must exist a point f prime of c, or a point c, such that f prime of c is equal to its average rate of change on the interval from -2 to 2. Okay, I'm not going to write that there, though. I'm just highlighting that's why we're calculating this. So, we start out by calculating the average rate of change just by plugging some stuff in. I'll skip the tedious calculations. We all have calculators and computers to do this stuff for us. We put in 2 to f of x, and we get out 11. We put in -2, we get out -9. And then we just take 11 minus -9 over 2 minus -2, and a little bit of arithmetic, and we get 5. So, based on the statement of the mean value theorem, what we're trying to do now, since we've shown that f does indeed satisfy the conditions of the mean value theorem on the interval from -2 to 2, what we're trying to do now is we're trying to find the points that the mean value theorem guarantees in the open interval from -2 to 2, i.e. points c, or x, where f prime of x is equal to 5, which is the average rate of change of the function on this closed interval. So we just differentiate f. Since f is a polynomial, we just use the power rule here. So 2x to the third minus 3x plus 1, take a derivative, you get 6x squared minus 3. So if we're solving f prime of x equals 5, we're solving 6x squared minus 3 equals 5. So I'll do this a little bit more carefully right here. 6x squared minus 3 equals 5 is the same as saying 6x squared equals 8. And that's the same as saying that x squared equals 8 over 6. Now, just a little bit of algebra, do a little bit of cancellation there, you get 4 over 3. X squared is 4 over 3. So, the points that are guaranteed to exist by the mean value theorem are the points x equals 2 over the square root of 3, and x equals -2 over the square root of 3. So we have to be a little tiny bit careful here. Remember, when you're solving x squared equals a number, you're gonna get a positive and a negative solution. So there are 2 points here. If we put them in a calculator, we get out something in the vicinity of plus or minus 1.15. These are the points the mean value theorem guarantees must exist. These are the places where the tangent lines to the graph of f of x have a slope of 5, i.e. they're places where f prime of x is equal to 5. Cool. All right, easy enough. So let's look at a graph really quick, just to get an intuition of what's going on here. Jumping on over, let's see. So I've already plotted out the function y equals 2x to the third minus 3x plus 1. I'm going to throw in -2 and 2 just to make it easy to see where we're drawing our boundaries. And I'm going to zoom in a little bit because this guy goes up for a ways and it's hard to see a little bit. So what basically is going on here is that between these endpoints over here, -2, 9, where this intersects, and over here, 2, 11, I should be able to find a tangent line whose slope is the same as the slope of the line from there to there. All right, and we can even plot this line if you want. Just remember quickly the point slope formula of a line. I have points, that's for sure. So y minus y1, let's use over here 2, 11. So that'll be y minus 11 equals, and I'll need my slope m here momentarily. I'll just leave it like that for the moment. But now I got to figure out what m is. So we're going from 2, 11 and or from minus 2, 9 to 2, 11, the rise, so from minus 9 up to 11, that's 20. And from minus 2 over to 2, that's a distance of 4. So 20 over 4 is 5. Bam. There we go. So this is the line we're looking for. I'm going to turn off these bounding lines on the side here just to make our lives a tiny bit easier and everything a bit cleaner to see. And I'm going to turn on the derivative. So I already put the derivative in there, and as I vary this slider, or the tangent lines formula, as I vary this slider, we're going to see, oh, there's one point where it looks to be just about parallel. And if I go the other way, there's another point, or just about. Hard to get this exactly precise with these little sliders, but just about parallel. So you can see that the mean value theorem did indeed do what it was supposed to. We got places where the slope of the tangent line is equal to the slope of the secant line, and those places occur within the interval that gives us the secant line, i.e. the secant line is from the endpoints from 2, 11 and minus 2, 9, and somewhere between minus 2 and 2, we pick up spots where the tangent line has the same slope as our secant line, somewhere around right there, and symmetrically about 0, somewhere around right here-ish. Close enough. You see what I'm saying. But there we go, mean value theorem. Cool. Okay, so we're pretty much done here. We've explored the mean value theorem and Rolle's theorem, and really they don't say anything that's all that crazy. It just says the obvious statement that if I had on average $100 in my bank account last month, then I better have had $100 at least some point. It says the obvious statement that if I drove an average of 50 miles an hour on my road trip, I better have driven at least 50 miles an hour at some time during the drive. Okay, but why do we even care? These are obvious statements. What on earth makes this interesting? Well, it's because there are a number of relatively strong consequences that come from this seemingly banal observation. For one, this tells us that a function with zero derivative has, or is constant. So if a function is f is differentiable and has a derivative of 0 at every point of some interval I, then f is constant on that interval. This tells us that there's no tricky way a function can vary, or there's no way a function can seem like it's not changing without actually doing that. There's no function that changes, but the derivative somehow misses it. The only functions that have zero derivatives at all points of an interval are functions which don't change on the interval. So derivatives really and truly do pick up change. If you don't change, you have zero derivative. And conversely, if you have zero derivative, you don't change. Okay, in exactly the same theme, we also get this cool result right here. If two functions, f and g, have the property that f prime of x is equal to g prime of x for all x in an interval, let's call it I, then f of x minus g of x is constant on the interval, where c is some constant, i.e. f of x minus g of x is equal to c. That is, f and g differ by at most a constant if their derivatives are the same. This theorem right here, this result, is a consequence of the first one. If f and g are both differentiable and f prime of x equals g prime of x for all x in an interval I, then f prime of x minus g prime of x is 0 at every point in the interval. We're just making a new function, let's call it h of x, which is equal to f of x minus g of x. Then h prime of x in the setting of theorem 6 would be equal to f prime of x minus g prime of x, and that would be 0 since f prime is equal to g prime. So, using theorem 5, this tells us that these guys are equal to some constant. F of x minus g of x is constant, i.e. h of x is a constant function because its derivative is 0. Okay. So theorem 6 is pretty straightforward to see that it's implied by theorem 5. But how is theorem 5 implied by the mean value theorem or by Rolle's theorem? Well, it's not too bad. So, since Rolle's theorem tells us that the average rate of change of a function on an interval is, or if the average rate of change of a function on an interval is 0, then at some point in the interval, the function's derivative must also be 0. Yeah, that's what Rolle's theorem tells us. So, if at every point of an interval, the function's derivative is 0, if here, and oops, not getting brush there. Here, let's just draw a function. I'm going to draw one that isn't constant. Yeah? There you go. If you can find two places where a function is not equal via the mean value theorem, you know that there's a place where the derivative is non-zero, i.e. from here over to here, the height of the function, the output, is not the same. So I can find, let's see, I'm going to see if I can draw a line through there. Good enough, close enough, close enough. I can find a place in here where the derivative is the same as the slope of that secant line. If the slope of that secant line is not equal to 0, then this is telling me that I'm picking up places where the derivative is non-zero. So, if you have a 0 derivative everywhere, it's telling you that stuff like this can't happen. i.e., if having two different outputs from your function, along with differentiability and continuity, implies that there are places where there are non-zero derivatives, then having a 0 derivative everywhere in the contrapositive tells you that you can't have different outputs. So, the mean value theorem, or if you want Rolle's theorem, they're really basically just the same thing, gives you theorem 5 just because having different outputs means that you have non-zero derivatives, at least for continuous and differentiable functions. Kind of cool. Some pretty strong results from a kind of obvious observation. But then again, that's pretty much all math is. And that's all we got for today. Have a good one.
おめでとう。
めでたいな。おめでとさん。